Okay, so today we'll sort of wrap up our ongoing discussion on convolution neural networks. So far, the idea was to build up intuition about what is a convolution neural network, how that further utilizes what is a original neural network or a fully connected network, and we went over all these different operations which are important to build a CNN, namely the filtering process, the process of max pooling, or subsampling is also sometimes that's the other word for max pooling. And then finally we looked at adding nonlinear layers as well, how you can stack them. Then we spent some time looking at some best practices to tune these choices or hyperparameters of the model. And then finally, I think towards the tail end of the previous lecture, I introduced some more terminology that you may have already seen before, specifically, what is an epoch, what is a batch size, and things like that. So today we have released the assignment 8, which is the first assignment of this final module. And essentially, this assignment is that you have to implement a convolution neural network. So I recall, originally when I polled and asked how many of you have already trained a network, it was kind of half and half, but this is your chance to train a neural network or a convolution neural network for a very simple problem, which has nothing to do with self-driving right now, but going on in the remainder of this course or the final 2 or 3 lectures, we will cover that aspect as well. So essentially, we have to implement in this assignment CNN, which classifies a given image either as a cross or a circle, exactly similar to sort of the example that we went over in the previous lecture. This is due in a week and a half, so there's the Thanksgiving break, and therefore I don't want you working throughout the break, so there's a slightly more number of days for you to attempt this. And I have provided some template code as always to get you started. Now, originally in this module, I wanted to cover the tool of choice for deep learning. There are many, many tools. And so I originally wanted to cover TensorFlow, but since due to my travel schedule, we skipped a couple of classes. We may not be able to go into the weeds of learning TensorFlow from scratch. Therefore, since we've been covering everything in Matlab, you already have that installed. I'm providing you a code in Matlab. If you prefer and you have a framework of your choice, PyTorch, TensorFlow, Caffe, what have you, you can still attempt this worksheet in whatever framework you want. You don't have to use Matlab, so I'm not going to force that on anyone, okay? Because the point is to learn training the CNN and not necessarily learning how to use Matlab. However, the template code is provided, and in the kind of the first half of this lecture, I just want to go over what you have to do in this assignment. You can always grab a hard copy at the end of the lecture today. So we'll go over everything that you have to do and what you have to submit, because it's a lot of detail. All right, so the objective is that we'll give you an image, and you have to build a CNN that will classify what is the pattern in that image. It would be either a cross or a circle. But not always, we've spent time talking about this as well. All crosses are not similar, same way all circles are not similar. So, for example, your image may look like this. Obviously, a human will classify this as a circle, and so should your CNN. Right? So what we have done is we've standardized all the images, so you have to do minimal to almost zero image processing, and you can focus mostly on the CNN architecture and the hyperparameter tuning and layering and the correct order of the layers and things like that, figuring out the padding and the stride and whatnot. So all images are 116 by 116 square pixel bitmap images. Bitmap just means that either a pixel has a value 0 or 1. If I recall correctly, all the white pixels have value 1 and the black pixels have value 0. You can also see that the circle actually has some thickness to it, which might not also be consistent in all the training images. So what is provided to you is a data set of 900 images of each of the 2 categories. So, and we also provide you some template code for setting up the training and evaluating your CNN. But you have to fill in, like with the other assignments, a lot of the missing stuff in the template code. So I just want to go over you can think of it as a semi-tutorial of doing CNN in Matlab / telling you about the homework assignment. I didn't want to risk starting Matlab on this slow machine, so I just created slides for every step of the code. Okay. So what is provided to you is simply two things. You have a folder called training data, and we are providing you a template called basic CNN. And also within the training data, there are simply two subfolders called circles and crosses. The data itself is, I think, less than 5 MB, so it's not like huge amounts of data. In fact, the CNN you will build is not going to be too deep or will have tens of thousands of parameters. So it can even be trained on a CPU. You don't need like a workhorse or a multi-GPU machine to do this assignment. So each of these subfolders has nothing but images which are uniquely named. So they are conveniently actually named in order from 1 to 900. And these are 900 images of circles. You can actually see, some of them are not technically circles. They are ovals or whatever, ellipses, and incomplete. Some of them just contain arcs actually. But they're all present in this folder called circles. Similarly, we have a folder called crosses. You have 900 images which are provided. So this is all the data that is provided to you, and you will split it into validation and whatnot to do this assignment, and we'll go over that. Then the code which is provided is called basic CNN template. It's a single MATLAB script which does all of what is needed to do in this assignment. In particular, it does 6 different things, starting from you can have some high-level control variables that I'll show you in a bit that will control the execution of the entire script. Because it can, based on some certain flag values, some things will occur and some will not. That's how this code has been structured. Then from steps 2 to 5 is really what the assignment is about. Loading and preparing the data, then you set up the architecture. That's something you will do. You will train the network and you will report on the results in many, many different ways. And then as always, I've provided some code base that you can enable or disable to generate certain plots, right? Just like the previous building sort of homework. Okay, so let's look at the first one. So at the beginning of the code, you will see this flag called do training. Oops. Maybe this one will work. Oh, okay. Yeah, all that effort to just point towards do training, right? So you will have this flag called do training, and that is by default set to true. What this flag is controlling is that if it's set to false, then your network will not train. And it will become clear if you download the template. Why would you not train a network is because after you train a network in MATLAB, you can save the entire network as a mat file, just like a mat object. So in certain passes, when you are more interested in probing and looking at the intermediate filters and features of your network, you may not have to train every time to reach that stage. So in that case, when this is set to false, the code looks for an existing mat file with a particular name and just sort of imports the pre-trained network to do all of the plotting and the evaluation. So, but for the first time, you have to set it to true because I haven't provided a pre-trained network, obviously, because that will defeat the purpose of the assignment. Then there are other flags. You can see, we have flags that will control what plots are generated. And you have to be kind of mindful about setting them all to true because it will generate hundreds of plots, okay? So we'll go over each one of them on what specific sections of plotting are generated, but this is what I meant by the control flow or controlling the execution of the code. Obviously, if you're writing your own code in PyTorch or whatever, you don't have to worry about this. The second part is loading and preparing the data, and so let me just go over the steps and then I'll dissect each one of them and also tell you how MATLAB handles each one of these functions. The very first function is called creating what is called an image data store, right? So we are calling image data store, and if we notice what we are passing is, we are passing it the name of the folder which contains the training data. We are setting an option of include the subfolders to be true because our directory is structured such that the data is actually contained in subfolders. I am informing the data store that all the extensions are bitmap.bmp. And finally, I'm also telling, here's where the magic happens. I'm saying that whatever images are present in one of the subfolders, just give them the label of the name of the subfolder. Okay, so if we have 900 images present inside the circles subfolder, all those images will get the label circles just because of this single command. Okay, so we will go over how this works in just a second, but we create this image data store object, and if you are familiar with other deep learning libraries, they also have to do similar step where they need some sort of a dictionary or a data store to access the images. Then here we have just some variables which log the channel information. What is meant by channel? Channel is how many, whether your image is a single 2D matrix or it has 3 different channels like RGB. In our case, the channel is just 1 because our image is bitmap, so it's pretty obvious. And the number of label categories for us would be 2, either circles or crosses. So that information is just getting read from the image data store. Then you can very easily, again, there's a function just like other deep learning frameworks. You can call your data store and partition it into 2 different data sets. Now here I'm calling the other one validation. It's up to me whether I call it training or testing, or I can give it whatever label. So what I'm doing, maybe going here is better, but yeah. So here is, we are using a function called split each label, and we are passing it the name of the data store, how much to split or the proportion, and we have an option called randomize, which, as you can imagine, it's not like we are just taking the top 0.7 fraction of the data. It's actually 0.7 fraction but randomly selected, and that shouldn't affect us because each of our images are sort of independent of the other. Okay, so they're not related in any sense. So if you do this for our data set, we had 900 images with 0.7, you get this much in training and 270 for validation. And it actually might seem that 600 images are not enough, because I think people have the, I shouldn't call it misconception, but people have the perception that you need thousands or millions of images to train deep neural networks. We'll see instances of that where that is true, but that's not true for all neural networks. Okay, actually for this simple network, hundreds of images are more than enough to get a very good accuracy. So the thing which you may not be familiar with is what is this data store. So let me just show you some pictures to make that clear, and then I can take some questions. So let's say you have all these images which are stored on your local hard drive. Now we've seen this before. The problem is that maybe that problem doesn't occur for our data set, but in general, if your data set is large and the total sort of size of your data or memory size of your data is greater than the RAM of your machine, you cannot import or store all the data and do the forward and backward pass, right? Because for each forward and backward pass, you are also storing the values of the weights in addition to the input, raw input, plus you are storing the gradients of the backprop. So let's say your image had a size of X megabytes. When you actually load it and do the forward and training pass, it's going to become some multiple of X, and that multiple is greater than 1. So what instead we do is we let the images remain in the hard drive or the storage of your machine, and we just create a library, like it's a linked library called the data store object. And what that is doing is it's just linking to the folder on your machine where these images are, and it's creating this kind of a pointer, if you will, to that space, and only what is requested is loaded into the memory. And we have seen before that what is requested can be controlled by specifying some hyperparameters like batch size and number of epochs and things like that. So the point is that you don't really need to have all the images in the memory at once. There's a read operation that will access whatever is required. And so all of this underneath the hood machinery is handled by image data store, in addition to also assigning labels to these images, which is just convenient because our original training data folder was structured in a sense that image data store as a function can read that. Okay, so this is what allows us to very easily create this data store object without loading anything into memory. Finally, we had a function called split each label, which is responsible for splitting this data store object into, let's say, training and validation. That is also being done in a pointer manner. this is not actually, that we are storing some training separately and validation separately. We are simply creating another, using another function to tell the image data store which images or the names of which images are to be present in your training samples and which images belong to the testing sample. So it's actually, very well handled in some sense. So I hope that is clear that this is the very first, well, not the first step. The first step was controlling the execution, but this is the first step in terms of training your CNN is to just process this image data, load the image data, not process it. So any questions so far? Okay, so let's keep going on what you have to do for the assignment. You have to do step 3, which is you have to set up the CNN architecture, and that's again specific to how Matlab handles that, so I will go over this, but you are not, I will come later address that, how do you submit your solution if you are not using Matlab. But right now, let's keep going. So the second, the main part of the assignment is setting up the architecture for the CNN. And so what we do is we begin with some definitions of, what is the size of the filter I want. So I have just chosen some size over here, and again, I'm having problems, sorry. I have chosen some size, forget it. I've chosen some size of filter, which is 10 by 10 here, but you can obviously change that, right? We've seen in the example, you can use whatever, 3 by 3, 5 by 5. I've also declared a variable called number of filters. And so remember, each convolution operation doesn't just have one filter, it can have a stack of filters. And so you can, again, control however many filters you want by either dividing or multiplying this num filters by the appropriate value. But usually, the number of filters should be a power of 2. That's just a rule of thumb. And then finally, while we talk about setting up the CNN architecture, we have this function called image input layer, which is creating your first layer of the CNN, right? So remember, in any network, the first layer is just reading kind of the data. And so, it has essentially no weights because we are simply reading pixels. But in this case, the special property of this image input layer is that it can read a 116 by 116 square matrix, essentially, a bitmap image. Also, I want to highlight, if I can, I keep trying. Oh, great. So I want to highlight that, all of these, when you create a layer in Matlab, there's an option to choose the name of the layer. And I highly encourage you to name your layers because not only it will become easy to debug, but certain parts of the solution actually require you to show me a graph of all the layers of your network. And in Matlab, if you have named your layers, that graph is automatically generated. So if you read the comments on this image input layer, it says, the layer, we input a 2D image and then apply what is called data normalization. So this is something that I haven't discussed, so I want to take a small tangent to discuss what is meant by data normalization, especially in the context of images and in neural networks in general, and then we'll get back to our code again, right? So the idea is, let's say you have some data, right? So the plot on the left is the original data, and that original data is, let's say, number of samples n by the amount of features d, and here in this plot, we are only looking at 2D data, so we only have 2 features. So what normalization or zero centering does is, for each feature dimension, so for each dimension on the x and the y, I want to subtract the mean value along that dimension for my entire data. And by doing so, I'm ensuring that the mean of my shifted zero-centered data is always 0 in every dimension. Why do I do that? Can anyone answer that? Why do we care about zero-centering our data? Yeah, so the short answer is we want to remove any bias in a single feature vector, right? So at the end of the day, our network is dealing with gradients and values of neurons and inputs to the neurons. So let's say, along a certain dimension, you are plotting, square footage of a building, which will be on the order of thousands or in some cases hundreds of thousands. And in the second case, you are maybe plotting the number of rooms, right? So there's a big numerical discrepancy, and there's an unnecessary bias in the numerical value of one feature. And we don't want that to play a role in our backpropagation or any values of the gradients. So we zero center the data. In some cases, we also normalize the data, which is the third plot. And what is meant by that is you are enforcing not just that my means are zero in every feature dimension, but the scale of my data, the min and the max values are also consistent, right? So what you do is you can divide by the max minus min range, or in many cases, you just divide by the standard deviation. Yeah. Well, so we are just normalized. This is just the normalization step which is being shown. Right, so what you are saying is actually called whitening the data, and I don't want to get into that right now, okay? But you can actually have a uniform circle. So what that is doing is it's looking at getting rid of correlations, not necessarily the scale and the magnitude, okay, if it's a circle. Because here there's a definite linear sort of relationship between the two features. If you want to get rid of that, we can do what you suggest. So this is the intuition again about why we want to process any data before feeding it through the network. But how does this make sense in processing images? So here's a very simple toy example. We have hundreds of images of faces. Let's say we are building a network to detect whether where the face is, or whether it's a male or a female or what have you. So there's many steps to pre-processing. I think one of the questions which was also raised earlier was, well, what happens if your images are not squares, right? So we are always assuming that the input is a square matrix. So there's an extra step you can always do by center cropping all your images. Now this alone is can have its own sort of derivatives. So how do you make sure that when you crop the image, your subject of interest was in the center, or was it on the side? So it has its own sort of variations. But this is a kind of a simple heuristic way of making sure that you are agnostic to the actual size of your image. So what would zero centering and normalization mean in this image facial sort of database case? Well, here's what is plotted. It's probably better seen on this screen. On the left, I have plotted the mean of every pixel for the entire data. Okay, so for every pixel we have, or let's say we have 100 images. For every pixel across the 100 images, you are calculating the mean value of the color or the pixel. And that's what has been done for all pixels. So this is the average face which exists in my data set. On the right-hand side is the same calculation, but it's on standard deviation. Okay, so what the right-hand side, the more white the pixel is, the higher the standard deviation value. And actually, it's very interesting to see that most of the variance is in the background of the person and not near the face of the person, which is what you would expect in a data set. So what you can do is, this is your mean image in pixel space. You can go back to your training data and subtract this mean image from every image of your input. And that would be the same as zero centering your image now. And likewise, if you want to normalize the values of the color in your image as well, you can divide it by the value of the pixels in the standard deviation image too. So when you do that, maybe it's not that visible, but your input images slightly, you can think of it that they're getting blurred, but what actually is that we are getting rid of any bias in our data. It's the zero centered now. So for every pixel across this new data, the mean would be 0. And if you divide by the standard deviation, it would be normalized. So this is what is called zero centered normalization. And why did we go down this rabbit hole? Because the input 2D image layer in Matlab does zero centering. In our case, we have bitmap images, so zero centering is not that big of a deal. Our values of pixels are already like 0 and 1. But I just wanted to cover this because it exists in the code. So let's look at what you have to do. You have to fill in all the rest of the layers of the network. Okay, so some examples are shown here that you'll call a convolution 2D layer. And then you have to pass it some arguments. The arguments would be, I'm just guessing, I don't recall MATLAB's exact syntax, but it would be what is the number of filters in this convolution layer, what is the size of each filter, and whether or not you are applying some padding, and what's the stride of the convolution as well. Right, so the 4 things that we covered last time. Then you can call a ReLU layer, a max pooling 2D layer. These are all pre-built functions. You are not writing them. You're just calling them with the correct sort of arguments. And I have just shown you the names of the functions or suggested some names. You are free to choose more. And then you have to repeat these operations in some smart way to actually build your network. So to help you with that, I haven't shown you the best performing network, but here is one option to get you started, at least. Okay, so you can use these sequence of layers. So you can define, in this case, from 2 to, let's say, 10, we have a convolution, ReLU, pooling, followed by the same sequence, followed by the same sequence. So it's repeated thrice. But if you look at the right-hand comments of each of these layers, it's also telling you how many filters were used, what was the size of the filter, what was the stride and the padding in this example. So this is what I call like the benchmark CNN. Everybody, regardless of whether you are using Matlab or not, if you use this architecture, you would have a certain performance on this data. But don't restrict yourself to just this architecture. The whole point is to try different things, try different filter sizes and whatnot. Okay, so I don't want to just replicate documentation, but this is where you have to look in order to, if you want to be creative in adding more layers, or if you don't want to see how you use an existing layer. So, Matlab provides these functions called convolution 2D, fully connected layers. It provides us ReLU. Remember how we spent some 5 minutes on different activation functions of leaky ReLU and exponential ReLU or ELU layer. So all of those can be added based on how you see fit. We have many options for pooling as well. So I emphasize that max pooling is the most straightforward thing, but you could do average pooling, you could do sum pooling. All those options are available. So you have to fill in these layers, and the thing to remember is that the layers will get attached in the order in which you declare them with the correct options. If there's any mismatch between the output of one and the input of the other, you will get a warning or an error. And then finally, those were the middle layers. The input layer was just the image 2D thing. I've already also specified some final layers for you, so you don't have to worry about sort of closing the network. You just worry about the image feature part or the CNN part. And so in this case, there's a fully connected layer at the end of all of our ReLU and pooling steps. Then there's a softmax layer that we also discussed, which will convert logit scores into probabilities. And the last layer is actually calculating the loss, right? So we need a layer which will actually calculate the loss that will be backpropagated through the stochastic gradient descent. And so once you have all these sort of structures, of the layers, then you can create an object at the very bottom where it's just stacking the input, middle, and final layers together. So any questions on how does, well, let me say the question is, is it clear how Matlab handles layers and how do you stack them? Okay, so it's actually very straightforward, and it's very similar to how other deep learning frameworks also do this. In some frameworks, you don't have to specify every layer separately. You can just say, I want to do convolution followed by ReLU followed by pooling in one line. So that's useful. Yeah.
We don't have to change all the final layers. Where would you have to specify that using the cross-section?
Sorry?
If we don't have to change this part, where do we have to indicate we can use the cross-section?
In the last layer. So the classification layer in Matlab uses cross-entropy by default. Yeah. Yeah, you can change it to some other index as well, but entropy loss, by the way, is simply comparing your logic scores to the ground truth in a smart way. Okay, so all layers are stacked together. Okay, so we know how to load the data, now how to set up the network. Then you actually train the network, and so for training, we already have seen the one thing you have to do is specify the initial guess of your weights, and they all cannot be same, they all cannot be 0. In fact, we also saw that usually for a very deep network, they all cannot be very close to 0 as well. This network is somewhat simple, so you can use weights which have been provided. So what has been provided is essentially we are choosing randomly from a normal distribution which has a standard deviation very, very close to 0. Okay, but it's still random. So we will choose some weights, and then you will specify some options for your solver, right? So in particular, I want you to try some suggestions. Again, the details of the suggestions are in the actual worksheet, but you have to play with what is the momentum, and we studied, what is the momentum for stochastic gradient descent. It's essentially telling you how close you want to be with your previous velocity or direction of the loss, sort of decreasing the loss, or you want to deviate to a large extent. So by default, anything which has been initialized to 0 is something you have to fill in. Okay, if you just remain that keep that at 0, then no learning will happen. You have to also specify your learning rate, which is once you have the steepest descent, how much do you actually move? And so again, some more specific values are present in the worksheet, and you have to play with the number of epochs that you train your data on. In fact, this is let me give you like already a hint. This is going to determine a lot of your accuracy, because remember how I said that we only have maybe 600 or 700 or so images left in our training after the proportioning it out. It's the number of epochs on how often you see the entire batch of 700 images, which is leading to the improvement of the network. So play with epochs generously. And so the last line, or the second to last line, is where the training happens in this. And I have tried it already on a regular sort of i7 CPU, not a GPU. It should actually take 6 minutes, but no more than 10 minutes if you're not running other intensive operations. So in the next week's lectures, I will talk about GPU aspects of deep learning, specifically as they apply to autonomous vehicles. It's a very important area. It's sort of out of the scope of the modeling side, but we will still look at it. But for this problem, a CPU is fine. Okay. And the last line is actually what saves the network, which I'm calling ExoNet, or Circle Zero Cross and Zero Net, as a mat object, right? So it will only get saved the first time it gets trained, and then the next time you can use it for plotting. Or one of the things you might see is you can restart the training from the weights of the previous network that you have learned, right? So instead of randomly initializing the weights, you can load a network, look at its weights, and restart training, maybe with a different architecture or something like that. Okay, so play with that. So just to show you how this object appears in Matlab, this is a network called AlexNet. We will hopefully have time to go over some of these properties today. And so what I'm showing is the layers in AlexNet. And it's a little bit hard to see because the font is small, but essentially we have sort of the similar stack of layers. We have convolution followed by ReLU. We have max pooling. There's something called normalization, which is actually not used anymore. It was used back in the day when AlexNet was designed. But essentially we have these sort of a block of convolution, ReLU, and max pooling repeated after each other, which is the main part of the CNN. So the input to AlexNet were images of the size 227 by 227 by 3, so RGB. Because this was trained on the ImageNet data, which I also want to talk a little bit about today. So this is the kind of inspiration for your network as well. It's obviously not as deep, and the input image space is also much simpler for us. So this is the essential part where the images are getting converted through these series of operations of convolution and max pooling and ReLU or other nonlinear filters into features. And then these features are flattened out as inputs to a fully connected layer, similar to our example in the previous lecture. Then we have a softmax layer, which converts the output of the fully connected neurons, which are logit scores, into probabilities. We've seen that too. And finally, we have a classification, or in this case, Matlab is calling this a classification. It's essentially the layer which computes the loss for the given input. Okay, so this is how your network should also appear, but not exactly like that. Also in Matlab, in the hyperparameters, I have provided some value of the batch size. You can play with that. If your laptop has a GPU, Matlab will automatically use the GPU. You don't have to do anything extra to train. But what is happening also in the code, even without the GPU, is that we are looking at all the training images now through the data store, and we are partitioning that into these batches, which Matlab calls mini batch. Okay, so we've seen what batches is, and in fact, when you run the code, one of the options is that, which I think you should switch it on, especially if you're using Matlab, is there's an option called verbose, and you set that to true. It's by default set to true in the template. It will start outputting all these iterations and how the loss is decreasing in every iteration and every epoch. It will start pushing or echoing all that data onto the console. And so what you should see, after the training, based on how many epochs you're training for, you'll see how much time was used. And then what you should see is it reports what is called a mini batch accuracy. So let's dissect that for a second. A batch is, remember, one proportion of your data that you want to do a forward pass on all the images in that batch. Let's say you have a batch size of 64 images. So you will calculate the loss of all 64 images before you do a backpropagation update to adjust the weights of your network. So what this column is telling you is what was the mini batch accuracy for all sort of batches, or the mean accuracy for all the batches in that epoch. And what you should notice is that this should decrease if your network is actually learning something. And what is reported on the other column is the pure value of the loss. So accuracy is how, if you are predicting the correct label, and loss is the actual loss calculated by the last layer of your network. In fact, what you may see, and if you get puzzled, that's why I wanted to show these screenshots, you may see that after some point towards the tail end, your batch accuracy is 100%, which may be a sign of overfitting. But if you look at the loss, it's actually decreasing. It's still decreasing until it starts increasing again. Right? So maybe I should point that out. So I'm talking about this part where the batch accuracy is not improving anymore, but the loss is changing. And this is an indication for choosing the correct number of epochs to look at whether you are overfitting the model or not. Okay, this is one of the hints. So essentially what the training is doing is you have three things which dictate how good your network is. The architecture of the network that you want to play with. I have given you a baseline to get started. Training data you don't have much control over. It's given to you. And finally some training algorithm options, which you also have to play with. Right, so in fact, what I'm encouraging you to do is play with the CNN architecture and choose one which works, and then play with the options to get the best results. And the two options which should really affect this the most are learning rate and momentum. So any questions on the training part? Okay. All right, so let's keep going. The final piece is you have to test the performance of the CNN. So again, there's a convenient function called classify, where the input is the CNN object or the name of the network. You pass it the data set on which you want to test the accuracy. And again, you can choose a batch size for better computation. But what this is going to give you is the predictions of the network on the validation set, which was the 0.3 part that we didn't train on. So something else that you may be seeing for the first time, we compute what is called the confusion matrix, which is another way of looking at the accuracy of your network. And what by default the code is reporting is the mean accuracy of the network, which is a property of the confusion matrix. So if you haven't seen confusion matrix before, here's a quick 101 crash tutorial. So at the end of the day, you have a network, and you are going to generate a response to a given image which has a ground truth, which was part of the validation set. Right? So you are generating some predictions, and some of the predictions will be correct, some will be incorrect, and so that's what's being shown here. where we have, I guess 3 categories, yellow, black, and blue, and your predictions are on the right. So what you can think of this as, you can plot a matrix such that the rows of the matrix are the true labels or the observations, and the columns are your predictions. And the entries of this matrix are telling you that what was your prediction for a given ground truth, right? So if you look at the topmost value in this confusion matrix, the ground truth was a yellow box, and you predicted yellow twice correctly, right? I think it is literally following this example where you have sort of 6 correct predictions and 2 incorrect predictions. So you are simply saying, so let's look at the first error, which is the topmost row, the second entry in the topmost row is that the original label was yellow and you predicted blue, which is incorrect. So a confusion matrix is simply keeping track of all these possible combinations of what was the ground truth label and what did you predict. In your example for the homework, this will be a 2 by 2 matrix because we have 2 possible labels in the ground truth and 2 possible predictions. So what you can notice about this matrix is that the diagonal entries of this matrix are going to be the number of correct predictions. And so it makes it very easy for us to simply compute how many predictions did you get correct by summing up the diagonal. And that's sort of what is happening in this code. Okay? We are summing up the diagonal of the confusion matrix. Yeah, this is just another fancy way that you can look at the matrix as a heat map. So finally, the last part of the code, and although it has taken me quite a while to describe all of this, the code is just like 200 lines or something. So the final part of the code is I have given you options to switch on or control which plots to generate. And this can be done at the very top, but you can generate 3 types of images to improve your network. One is you want to look at examples of images which got wrongly classified. And so what that means is this code will tell you that here's the index or here's the image which was originally a circle, but you are classifying that as a cross. And that should tell you something about why that's the case, or is it tricky for a human to do that as well? And hopefully that'll give you some motivation to change. Or you can look at the effect of your momentum and learning rate on the number of images that you're getting wrong and which images. Is there a particular image which is always misbehaving? You may want to drop it out of training altogether and things like that. Then you can also plot the actual filters from each of the convolution layer, right? So remember, let's say in the example, we have 10 by 10 filters. Each filter can be thought of as an image. And what you want to confirm actually is that are the filters getting complicated enough in subsequent layers? So there's an option to view all the filters. Use that with caution because it will plot just filters for all the layers, and there could be many of them depending upon your depth and the number of features. And finally, we will plot what is called a feature map. And I haven't explained what that is. A feature map is, let's take an input image, let's say a circle. Let's pass it through each of the layers and look at what is the output of the convolution layer, right? So what we were calling like the filtered maps is what is being described in this slide as the feature map. So again, we want to see, in the first layer, maybe we are good at detecting the edges, or the features are getting, the feature maps show where the edges of the cross and the circle are, and subsequent sort of layers tell you more complicated patterns. You may want to see arcs in some of the feature maps and things like that. So here's an example of what this could lead to. So the reason I say use with caution is this is just a very small subset of all possible plots. But on the bottom left is an example with the yellow plots of wrongly classified. Okay, so what it is telling you is that that cross was wrongly classified as a circle for whatever reason. On the leftmost column of this slide, the circle and the cross shown, these are the inputs for which the feature maps are going to be generated. So let me try this again if this works. Yeah, so all of these are feature maps for these inputs. This is the wrongly classified stuff, and these are the filters on different layers. So is the distinction between filter and feature map clear? Okay, so you can plot all of this. Yeah. I think I have an animation to show you what a feature map is. So you have a filter, you convolve it over an image, you get a different feature map. Okay, so this is the red box and the green box, the small one, are your weights or the filters of the CNN layer. For any input, when you do the convolution process, you get a different feature map or filter map, and you can visualize that to see whether your features are getting recognized properly or not. And then once you have the features, you have to pass them through ReLU or rectified. For an actual image, that may look something like this, where the black pixels of your left image are negative values, the white are positive, and so 0 is gray. And so when you do a ReLU, you are getting rid of some noise in your kind of data. So you get cleaner edges. Someone had also asked, what is the effect of pooling on your sort of input? And so here I'm showing you that max pooling and sum pooling or average pooling will lead to different outputs. So it does affect what pooling layers you use. So this is also an example generated from the solution of the homework. I'm showing you 2 images, and I'm showing you some filters and the feature maps for these images all the way through the last layer. So you can generate all these plots by choosing the control flow variable for these. When you run the code, another plot will be automatically generated, which is the main loss function. And it's impossible to read this because of the font, but the plot on the top is showing you the accuracy per epoch. It's kind of it's plotting the stuff in the table that we've already sort of looked at. Right, so you can see for this particular network, after 10 epochs, you are very close to 100% accuracy, which was also shown in the table. And the plot in the bottom is telling you the loss or the error, which should be decreasing. In fact, you can see how it doesn't decrease for a while, which we saw that in the slide. That's an indication that the weights were not correctly chosen. So I could have done a better job so that the loss increases right away rather than this plateau first. Okay, so these are hints and things that you have to observe. And so in deep learning lingo, this is called babysitting your network. So you have to do that for this assignment. What do you have to submit? You have to submit a single file, upload the data as well. So keep the training data folder in the file. Definitely submit your solution to the template if you are using Matlab. Submit your best performing network as a mat file. Okay, so you have to submit your best performing network as a mat file. Then you have to also tell me what values you tried for momentum, learning weight, epochs, what worked best and what not. And when I say tell me, that doesn't mean just report those values. You have to justify them with some plots and some numbers. Okay. Yeah, so your solution should look something like this, but maybe not exactly this, because you should just send me 1 mat file, not 2. Okay, so let's talk about if you don't want to use Matlab. I don't want to force it to you. If you're already familiar with other deep learning frameworks, pick your favorite one. You can use it. Okay. So what do you have to do? You can use whatever framework you are comfortable with. One thing you have to do is should include requirements.txt file. If you are familiar with the pip install requirements, management of code, I've also shared the link where you can look at how to generate this file. Essentially, this file contains a list of all the packages and the dependencies that must exist for your code to run. Okay, and we'll run it. So don't worry about whether I have the correct Python or Anaconda or whatnot. We can run it, but you cannot leverage all this Matlab code to visualize the different stuff. That's something that I can't provide you. So you're left on your own if you are doing that. It may not be a completely bad thing because it's very easy to generate similar plots in other frameworks. However, what is very important is that you still have to provide a CNN, your best performing CNN, as a mat file, regardless of what you are using. And to do that, there is something called Open Neural Network Exchange, or ONNX. This is a standard way to encode a neural network model as a graph, essentially. while also preserving all the weights, the parameters of the optimizer and whatnot. So ONNX allows you to translate your neural network model from your choice of deep learning framework into a ONNX object. The Git tutorial is here. It supports nearly all popular frameworks. And then in Matlab, there's a command which can import ONNX into Matlab. So you still have to provide that mat file. The reason is because we are going to run an entire script. That's how we evaluate. We run your mat files across the entire class on test data as well. So you can use not Matlab for doing the assignment. Provide us your code with the requirements.txt file and provide a mat file. Those are the only two things. Okay, so that was all for the homework, by the way. I know it took us, I think, the most of the lecture. I didn't anticipate it'll take so long, but that's okay. So any questions on what do you have to do? That was clear, yeah. It's not the last homework. So this course doesn't have any exams, but this is due on December 5th, which is, I believe, the last time we will meet. But then there's a final homework that is still due, which will be released on the 5th. Okay, so it's not a lengthy homework. None of these homeworks are going to take you more than a week, simply put. But you can think of it that this homework has nothing to do with autonomous vehicles, but the module is about autonomous vehicles. So in the remainder of this course, I'm going to pick a problem in self-driving cars and modeling using CNNs. But you don't have to train a network from scratch. You will use transfer learning to solve a problem. So I will introduce what that is next week. Okay. All right. So what I had planned was, if you know me, I'm a big fan of looking at stories of, why something exists and why it came into existence and how is it useful for us. So even though we have, less time left in the lecture today than what I had accounted for, I think we can at least cover some of the story. And so I want to give you a little bit background of CNNs just to motivate and dissect some of the popular CNN architectures that I think if you are, again, in the business of being a cyber physicist and you use convolution neural networks for any image-related task, you will see these names again and again. So I want you to know why these networks became very popular and what do they do. So it all started with this big data set called ImageNet, which has really changed, and it was one of the reasons why deep learning became so popular. And it's actually funny to think about this because I was a grad student at the time. It's been 10 years since ImageNet was first sort of released, right? So in this computer vision and pattern recognition conference. And so it's a very, very well-cited paper. All academia and a lot of papers have been written using this data set. Actually, many startups owe their existence to this data set. So many, many businesses also spun off by building networks which perform well on image classification. And also in other domains, there's also equivalent of ImageNet. So you have something called medical ImageNet, which is looking at just medical images. MusicNet is a very interesting one. SpaceNet is looking at aerial images. So what the idea was that, we have to have a large-scale data set with examples, labeled examples of different types of objects, everyday objects. In fact, ImageNet became very popular and is very widely known for having a very large scale, millions of images for thousands of types of different objects. But it was not the first data set to do so. Before ImageNet in 2009, there were many other attempts at large scale data sets. So you may recognize some of them, especially the one on top right. MNIST is the most popular handwritten digits. It's become the hello world of deep learning and computer vision, and that's for those reasons I didn't even touch it in this course because there are millions of tutorials online on how to build a network using MNIST. But the idea was for ImageNet, that it was the first time when people really bought into this idea that we don't need to solve these classification vision tasks using human design features. Right? We can actually just look at examples and lots of examples and let the actual feature extraction part be automated through a convolution neural network. So while other networks were engrossed in a lot of detail of there's many very well annotated data sets where you are accounting for every pixel and every region, what class it belongs to, ImageNet became so popular and widely used because of scale, right? So we didn't care so much about the context and accuracy and labeling of every pixel, other than that, which objects are present in this image. So that's a much simpler task to sort of outsource. So just shown for kind of comparison, on the bottom left is the highest volume of data sets which existed prior to ImageNet were on the orders of tens of thousands to hundreds of thousands in one case. But in comparison, ImageNet is like 15 million and growing, right? So just like change the entire field literally, thanks to the work of a lot of graduate students and Amazon Mechanical Turk workers, which are responsible for generating much of this data. And the goal of this data, which was largely generated by academics, was that we should have a high resolution data set, which was also created by just mining the internet for images. Then the quality of annotations is what makes ImageNet very popular, right? So you don't just say that this image contains a dog. You have all possible annotations about what describes the object present in this image, and it's open source, right? So that's remarkable that a lot of funding has gone into maintaining and creating this data set, and then it's made available for free. A lot of, like I said, businesses have commercialized their models, which were trained on ImageNet. That happens even today. A lot of the self-driving cars owe their performance also to ImageNet, and I'll explain why by the end of this course. Right, so this is what made neural nets very popular. So this is what is called AlexNet. I think I've shown you one picture before. AlexNet was one of the first neural network architectures which really changed how well machine learning algorithms could perform on this classification task of thousands of objects on millions of images. Right, so this was the start, and then we had a lot of different iterations of from AlexNet to VGGNet and GoogleNet, and then ResNet is kind of the state of the art today. So really thinking back, we do have neural networks existed for a long time, and there were some advances in better architectures, better convolutions, ReLUs, max pooling, all that stuff. There was a parallel increase in the hardware side where GPUs became very popular to make the computation much more reliable and efficient, but really it was the data, and ImageNet is one of the biggest such data sets, which led to this whole field exploding in the last 10 years. And in fact, this is a recent paper which also shows that even today, for certain types of problem, more data does mean that your network performs better, right? So that is sort of the gist of this paper shown here. And so for the task of vehicle classification, which is what every self-driving prototype uses today, somewhere in there are features learned from this database of ImageNet, right? So we have, this is a dated slide, so we definitely have more than 1 million images of different vehicle types, but the interesting part is the annotations, right? The labeling is very rich. So you not only have whether this is a vehicle, you have what brand of vehicle is it, what model is it, what is the vehicle type or body type, or down to what trim it is or what year was that vehicle made in. So someone has gone through the process and collectively to annotate all of these things, which is what has led to us using this database today to make our vehicle detectors, which are behind the brains of many of the self-driving cars. So in the remaining time today, I want to give you some highlights of some of those neural networks. If you look at them, you will get to not only understand them better, but also have an appreciation for why they work the way they work. So kind of it all started even 10 years before ImageNet with the data set called MNIST from Jan LeCun. And so this network was called LINET, LINET 5 to be precise. And so now we understand, we should be able to understand everything in this image, right? So we start with a 32 by 32 input image, and then we apply 5 by 5 convolutions with stride 1. So in your head, you can simply say 32 minus 5 is 27, divided by stride of 1 is 27, plus 1 is 28. So the output at the next layer is 28 by 28. And it looks like we are applying 6 different filters. That's why we have a stack of 6 feature maps. Right? So then there's a subsampling, which is simply max pooling. Max pooling is 2 by 2 with a stride of 2. So you go from 28 by 28 to 14 by 14 because of stride of 2 and a 2 by 2 window. Then you again do a convolution, again with 5 by 5 and stride of 1. This time your input is 14 by 14, so 14 minus 5 is 9, plus 1 is 10, so the next layer is 10 by 10. You do another max pooling, you get 5 by 5. Now you have less enough features that you can flatten them out, do a fully connected stuff, and output this character. And this network was used for character recognition to look at what are the digits on checks so that banks can automatically read them, or USPS can automatically read the address on an envelope. Okay, so it's a simple convolution pool, convolution pool, convolution, fully connected layers. So this network existed before ImageNet, but it's what is called like a shallow network, or it's not that deep, right? So there's like 2 layers essentially of convolution. So if you look at the ImageNet data set, there's a long-running competition for what is the accuracy on that data set, right? So plotted here is from, you should read this plot from the right to the left. So prior to AlexNet, the accuracy was 25, the error was 25%. So a quarter of the guesses of the best at the time were wrong. And the AlexNet was the first CNN-based winner, which had a very significant gap in terms of reducing the error rate. Right? So we've seen AlexNet before. It uses a slightly deeper stack of the same convolution, max pooling value, and then you have some fully connected layers. This was the first time that ReLU were used in AlexNet. That was not used before that. And then you can also see some batch sizes and momentum rates that were the hyperparameters used at the time. Now, if you look at the image on the top right, it's a little bit weird because this doesn't look like a layer of neural networks. This looks like there's 2 parallel pipelines kind of going on, or 2 additional partition between the stacks of the network. That's only for implementation because at the time, GPUs were not that well tuned for this task. So we have 2 sort of parallel threads because the person, Alex, who built this network, AlexNet, had 2 different GPUs available. So he wanted to parallelize the training and the backprop of the network by changing the structure of the network. So AlexNet, by the way, reduced the error, which is shown on the very bottom, down to 15.4% from like 25-something%. That's why it's so popular. Next, the very next improvement was a network called ZFNet, which is the same as AlexNet, but with just the difference is the change in hyperparameters. So it shows you that on a task of predicting 1,000 objects on 1,000,000 images, just tuning hyperparameters also works. So what ZXNet does is, if you look at the text on the bottom of the slide, in AlexNet, we were using filters of size 11 by 11 with a stride of 4. So not only the filter is too large, the stride is like 4 pixels away. So in some sense, you are moving too kind of abruptly, and you're missing maybe some information or some patterns in the image. So ZFNet chose a smaller filter with 7 by 7, half the stride of 2. And then in some deeper layers, they just added more filters, right? So AlexNet used like 300 and 256 filters, and ZFNet just used 512 and 1,000 filters in some layers. So smaller filters, less stride, but more of them is what their trick was, to go from 15.4 to 14.8. So it might not seem that significant, but it's the best at the time in 2013. Also, I keep saying that ImageNet top 5 error. What that means is, when you look at the prediction in a 1,000 category problem, you look at the top 5 predictions, not just the top prediction. And if any of the top 5 predictions were present in the ground truth, you still categorize that as correctly labeled. Okay, because I think the top 1 error would be more still 25-20% in this case. So this was just like a marginal improvement to AlexNet. Then something interesting happened. We really built some deeper networks. And so both VGG and GoogleNet, they were the first networks to go below 10% in terms of their top 5 error. And so what VGGNet was, it's actually very clever in the sense, or very simple. Unlike ZF and AlexNet, VGGNet only uses 3x3 convolution with stride 1 and pad 1. It doesn't change the size of the filter for the entire network. And it always uses 2x2 max pool with stride 2. What it changed was just the depth of the network. So VGG16 had 16 layers, VGG19 had 19 layers. I think 16 was the one which performed the best. So it took the error to like 7.3%. But the beauty of VGG, which is still very popular today, and you will also hear about it when I talk about transfer learning, is in its simplicity. Single filter size, same stride, same padding, same pooling, just stacked at a larger depth compared to AlexNet or any networks before. A much more complex version of this is what is called the GoogleNet. And I won't go into too much detail about this, but their key idea is what is called the inception module, which is, you can think of it as, it's a small network within a network, inspired from the movie Inception, I guess. And so you have this inception module, which is essentially this network block, and what you see is a stack of these inception modules. And so each of these inception modules itself is a combination of many, many different convolution types. And so that's what led GoogleNet. We won't dissect it to the same extent as we have dissected others, because I want to get to the punchline, which is the state of the art today is a network called ResNet, which has also slightly been improved. But ResNet was the first network to go even less than 5% error, which is better than most humans on this data. And the secret to ResNet is we have gone from like 20 layers and 22 layers in GoogleNet and 19 layers in VGG19 to 152 layers in deep learning. Right, so very, very deep networks. It has 152 layers. And at the time in 2015, not so long ago, when these results were published, they not only outperformed any prior network in ImageNet, but they like outperformed all classification competitions at the time, just by having like a 10x more amount of layers. But it's not that simple, because here's a plot. What this shows you is we have a data set called Cypher 10. It's a simple data set with 10 object categories. If you actually train a CNN and keep increasing the number of layers, if you look at the solid and the dashed line is the training and the solid is the test error, it actually increases. A 56-layer network has higher error, both test and training, than a 20-layer network. So how is it that ResNet can have sort of a 10x more layers and still outperform with a significant margin? So the idea of ResNet is the following, and this is why it's very popular. So on the left is shown what, say, a regular 34-layer network would look like. And on the right is shown the equivalent of what that network would look like when it is a ResNet architecture. And so what sort of jumps across are these skipped connections, or these arrows which are going from some higher layer into an intermediate layer. And so I'll give you the intuition again, because sort of we are again at the brink of how much time we have. The idea is the following. It's actually very clever, right? So on the left image is what a regular network does, right? So you have some input X, it's image or whatever input. You have some multiplication with weights and or sum. You go through some nonlinearity, and then you output some function of X, right? That's essentially what has happened. You output h of X. In ResNet, what you output is not h of x, but you output, or you're trying to learn a function f of x such that it will be added back to the original input x, right? So this skip layer, let's see if this works. Okay, no. So the skip layer, we are taking the input x and directly jumping 2 layers, and then there's an addition operation. So what is the layer learning in between? We are still learning some h of x, but since the requirement is that the output will be added back to the original value of the input, we are only learning what is called the residual. So we are learning some feature or residual feature f of x such that when it is added back to the input, we get the sort of the h of x map, or the rich feature map. So this is what allows you to go deeper in terms of the number of layers, while avoiding this observation that doesn't necessarily correlate with reducing the error. So you are reducing the burden of learning by saying just learn the residuals between these layers, and don't have to learn and overly complicate all these features unnecessarily. So I know that was a quick overview, but at least I'll give you some insight if you were to ever go and read this paper. Okay, so with that, we can come to the end of our discussion on convolution neural networks, how they work. After this homework, you will have implemented them, whether in Matlab or in other framework is up to you. And so in the remaining 2 lectures of this course, I want to revisit the problem of self-driving. Right? That's the theme of this module. And in particular, we will pick a problem, either vehicle detection or lane detection. And then I will show you a trick that you may have seen before called transfer learning, where you will use a pre-existing network like VGG16 or AlexNet, and you will perform what is called a network surgery on them. You will replace some of the layers with your own data, and then you train on your own subset of data. Because what these networks have done on ImageNet is nature is compositional, and these networks have learned how everyday objects appear. That's what the information in these layers are, right? So everyday objects are made up of edges and patterns and textures, and that information is already present in AlexNet, in VGG16, trained on millions of images for thousands of categories. So the idea of transfer learning is, let's take this pre-trained network, remove just the fully connected layer, substitute it for your own task, and just retrain the fully connected layer while leveraging the feature extraction or the feature map of these deep networks. And that's what is used all the time to build these individual perception pieces. There is no equivalent of ImageNet for pedestrians or cyclists or cars. Okay? While we are generating more and more data and labeling that, a lot of the roots of all these perception networks that we discussed in the first lecture of this module are used and built with transfer learning. So that's the final piece that we'll cover next week. Today, I just wanted to cover CNNs and the homework. So this is due not in a week, but in a week and a half. So I hope everybody enjoys their Thanksgiving break, and I will see you next week.